Greetings all. Question: what the heck is delta G? First of all, the triangle thingy is the Greek letter delta, which we use to indicate that something is changing. And in this case, what's changing is the Gibbs energy, and Gibbs energy is what we're representing by the letter G. Well then, what the heck is Gibbs energy? The Gibbs energy is the amount of energy that is available to do work. That's not the total amount of energy. The Gibbs energy is what's left over after the second law of thermodynamics has taken its slice out of the total energy. While we're here, because of the unfortunate fact that we scientists love to give things 2 or 3 different names for the same concept, you'll also hear the Gibbs energy referred to as the free energy, or sometimes as the Gibbs free energy. The IUPAC says the preferred terminology is Gibbs energy, named after a dead person, Josiah Willard Gibbs. I'm not a huge fan of the term free energy in any case because free energy definitely is not free. Actually, Gibbs energy is like money because we can use Gibbs energy to pay for things. The delta G, the change in Gibbs energy, tells us if this particular process or reaction is the kind that releases energy, and if it's the kind where we can use that energy to do work, or whether this is the kind of process or reaction that costs energy. Let's look at a simple example. Let's say I have some propane and I'm going to set that propane on fire. Then I'm going to use the energy coming off of that fire to do work. Like, for example, grilling a cheeseburger, or as the vegan option, roasting an apple or something. Here's the chemical equation for the combustion of propane. The carbon atoms in the propane get fully oxidized to make carbon dioxide, and the hydrogen atoms in the propane get fully oxidized to make water molecules. The propane and the oxygen are the reactants, and the carbon dioxide plus the water are the products. I know I can burn propane. I know I cannot burn carbon dioxide and water. Therefore, there must be more Gibbs energy in the propane plus oxygen than there is in the carbon dioxide plus water, because that difference in Gibbs energy is what we see as the energy on the right-hand side of the chemical equation. That's the energy that I'm going to use to do the work required to grill my cheeseburger. When we do the arithmetic to calculate delta G, our rule is that we take the Gibbs energy of the products, where we ended up, and subtract the Gibbs energy of the reactants, which is where we started. Delta G is always products minus reactants. If the Gibbs energy of the carbon dioxide plus water is less than the Gibbs energy of the propane plus oxygen, and we just tried to convince ourselves that it is, then the delta G for the combustion of propane is a negative number. We have some fancy scientific words to describe that. When a reaction has a negative value for delta G, we can say that reaction is exergonic, where X is like exit and erg is like energy. We can also say that reaction is spontaneous. We can say it's a favorable reaction. We can say that's a reaction that can do work. Or, if we want to use a somewhat imperfect economics analogy, we can say that the combustion of propane is a profitable reaction. And, the other way, when a reaction has a positive delta G, we can say that reaction is endergonic, where endo like into. We can also say that reaction is not spontaneous. We can say that reaction is an unfavorable reaction. If this is a reaction that we want to have happen, then some other process has to do work to put energy into our reaction. Or, to continue to use our economics analogy, a reaction with a positive delta G is a reaction that costs money. Okay, well that wasn't too bad. Is every chemical reaction relatively simple, like the combustion of propane? Well, of course it isn't. A lot of the reactions in biochemistry cost energy, and in that case some other process or reaction has to release enough energy to drive the expensive reaction that we want to have happen. Another example then. Let's look at these two chemicals here. The one on the left is 2-phosphoglycerate, and the one on the right is 3-phosphoglycerate. You can see just by looking at those chemical structures, these are very similar chemicals. They have the same inventory of parts. The atoms are just arranged a little bit differently. We have a magic word for that. These are isomers of each other. If you're willing to trust me on this for right now, these two chemicals can switch back and forth between these structures. 2-phosphoglycerate can turn into 3-phosphoglycerate, and 3-phosphoglycerate can turn into 2-phosphoglycerate. The fancy scientific word for that is this is a reversible reaction. In glycolysis, which is a metabolic pathway that breaks down glucose to start getting energy out of the food we eat, in glycolysis the reaction goes in this direction, 3-phosphoglycerate to 2-phosphoglycerate. Gluconeogenesis is another metabolic pathway. We can use gluconeogenesis to make new glucose molecules from various scraps and leftovers floating around in the bloodstream. And in gluconeogenesis, the reaction goes in the other direction, 2-phosphoglycerate to 3-phosphoglycerate. That means there must be some set of conditions where 3-phosphoglycerate to 2-phosphoglycerate is spontaneous, and another set of conditions when 2-phosphoglycerate to 3-phosphoglycerate is spontaneous. This is an important point, actually. Delta G is not a constant. Delta G is not a fixed number. The delta G of a reaction can change from day to day and from moment to moment, depending upon what the conditions are in this system at this particular moment. Some set of conditions makes the reaction 3-phosphoglycerate to 2-phosphoglycerate have a negative delta G. And under that set of conditions, 2-phosphoglycerate to 3-phosphoglycerate will have a positive delta G. Some other set of conditions makes the reaction 2-phosphoglycerate to 3-phosphoglycerate have a negative delta G, and under that set of conditions, 3-phosphoglycerate to 2-phosphoglycerate has a positive delta G. Positive and negative, we've done both of those. Is there a set of conditions where the delta G for this reaction is exactly equal to 0? Yeah, actually. When the delta G of a reversible reaction is exactly equal to 0, that reaction is at equilibrium. In the next video, we'll start talking about how we find out where equilibrium is and what kinds of conditions we need to make a reaction exergonic or endergonic. In the meantime, thanks very much, and I'll talk to you next time.